Hi, today I'd like to show you how to use the Solartron Model 1250, and this is it over here. So I'm going to show you how to use this to run a frequency response plot of a first order low pass filter. So I'm going to show you how to set it up from it being initialized. So first we're going to initialize it. So to initialize it, we hit the self-test and this init, and that initializes, it sets everything to the default conditions. So we're going to run a frequency response from 0.1 to 100 hertz, and our amplitude is going to be plus or minus 1 volt. So the way we set it up is first, we put our initial frequency in there of 1.1 hertz, and our amplitude is going to be 0.707. That's RMS, which gives us the 1 volt amplitude. So in our analyzer, we want to set our integration time to 2 seconds. So on our data output, we want to display all. We want to send the data to the RS423 because we are using a serial interface to collect the data. And over here on our display, our source is going to be channel 2 over channel 1. So we're going to hit enter there, and our coordinates are going to be log r theta, and we're going to hit enter there. So I believe that's our basic setups. And when I'm ready to run the frequency response, I'll show you how that's done. So I'm going to show some of our other setups here. And what I have is I made an op amp board, I call it. It's just a bunch of op amps, just typical ones like followers, differential amps. And so what I have is a low pass filter is over here, and what I do is I make a printed circuit board and then I break it all out to a piece of wood that has the schematics on it with nails, so I could just put clips on it to kind of make any kind of circuit I might need for my just for general use around the lab. So I have an inverting op amp here with a gain of 1, and I have a capacitor. This is the capacitor over here. On clips, it's just a 0.1 microfarad capacitor, and we'll go through the circuit a little bit. This is it over here, but we'll go through it in a little bit of detail. It's just basically a low pass filter. The other thing I have here is this power supply. It's a dual power supply set for plus or minus 15 volts, and it's a HP 6205C dual DC power supply, and I'm using that to power the op amps to provide the plus or minus 15 volts for the op amps. So this is the back of the Solartron, and I'm using the serial interface over here that I have connected to a computer where I'm going to use Terraterm, and that's so I could collect the frequency response data. So this is the back of the PC where the other end of the serial interface goes to RS232. So I'm just using COM port 1 into the Dell computer so I could collect the data. So this is Terraterm, and if I hit the break key, I'm going to hit the break key on the Solartron just to verify that we're connected. So when I hit that, I get a break-in. So that tells me that my serial interface is connected. So now I'm going to show you how to do the frequency sweep. So to do this sweep, I hit on the generator, I hit start, and then analyzer, I hit recycle, and then on the sweep, I hit start continue. There's one other thing I have to do here. On the sweep, I have to set up the sweep. So I want my minimum frequency to be 0.1 hertz. Oops, hit the clear, so 0.1, enter. I want my maximum frequency to be 100 hertz. So I hit 100, enter, and I want my delta log to be 10. I want like 10 samples per decade, 10 points per decade. So now to run it, I just hit the generator start, I hit recycle, and I hit sweep, start, continue, and I want to hit log going up. So I'm going to start from 0.1 to 100 hertz. So that's at 0.1, Let's see if it switches to the next frequency. So it's going to take at least one cycle or 10 seconds to do the first point. So I'm hoping that it's going to sweep. Okay, so now I want to 1.2598 millihertz. And now it's doing the sweep, so it's close to 0.2 hertz. And you can see the sweep, it's 0 dB. It's like close to plus 180 degrees, the phase, because it's an inverting op amp. So we're approaching 1 hertz there now. So this is how it does a sweep. And we'll do this again also to show you how it collects the data on the computer. So now it's at 3.1623 hertz. It's minus 0.33 dB. So you could kind of see real time. You could see it analyzing the data. So this is really great for doing electrical circuits, the frequency response, and also really good for testing actuators and speakers. Right now we're just doing a simple op amp low pass filter. So we're going to go up to 100 hertz, and the last point's 100 hertz, so we have minus 15.56 dB and plus 100 degrees. So we're going to stop it at the end. So hit stop at 0. So now I'm going to repeat the frequency sweep just to show you how it collects the data. And so it should takes about maybe 3 minutes to do a 0.1 to 100 hertz sweep. And the way it works, we set that integration time to 2 seconds. So it's either going to take 2 seconds or 1 cycle, whichever is the longest. So there you go. There's our 0.1 hertz. That's our 0.1 hertz sample. And with a low pass filter, the dB is close to 0, and it's about 180 degrees because of the inversion. If it was a non-inverting op amp, it would be around 0 degrees. So there it goes. You could see it collecting the data there. It's up to 0.251 hertz, and it's going to sweep up and do 10. I found that 10 points per decade is pretty good. If you want tighter resolution, yeah, you can do say 20. And so now it's running faster. It's going to do one every 2 seconds because I set that integration time to 2. But if it takes longer than 1 cycle, then it's going to take the time to do the 1 cycle. So say for the 0.1 hertz, it's going to take at least 10 seconds for it to analyze it. So it uses in-phase and quadrature method to figure out the frequency response. If you read the manual for the Model 1250 Schlumberger Solartron frequency response analyzer, it goes into the details of how it does that measurement, doing in-phase and quadrature. These days we don't use it too much. You could do some of this stuff using possibly like MATLAB and post-process it and do it in-phase and quadrature on data. So there you go. We got our 100 hertz point there, which is the minus 15 dB at 100 degrees. So we're going to stop it at that point. So I'm going to hit stop at 0. Generator stopped. So I wanted to show you how to get the data. You can either turn on the log feature or a Solartron and start it from a file, or this one, since it's so small, we can make a text file here. So we make new text document, and we'll call it freak response to .text. So we'll just open this up, and we could cut and paste it from Solartron here. So we just want 0.1 to 100. So we'll hit OK there. Oops. Didn't want to do that, but all I really want to do is copy and go to this file here and then paste it in here. So it's in there now, and we could save it, and then we can use Excel to make a frequency response plot out of it, which we'll go through that real soon. Okay, so now we're going to talk about what to do with this data we just collected from the frequency response analyzer. So I have a little write-up here using the Solartron 1250 to test a first order low pass filter. So a video will be made to show how to use a Solartron 1250 frequency response analyzer to test a first order low pass filter made from an inverting op amp. So the filter has the form 1 over RCS plus 1, so R is a resistor and C is a capacitor. And notice the minus sign because it's an inverting op amp. So in our test case, the test we just ran, our resistor is 100 kilo ohms, so that's 100,000 ohms, and our capacitor is 0.1 microfarads. So if you multiply R times C here, that's our tau, that's our first order time constant. So tau is considered the first order time constant. So our tau is 0.01 seconds. Okay, so this is if you take one, if you invert that, if you take 1 over 0.01, you get 100. So this is a tau equals 1 over 0.01 seconds, which is 100 radians per second. So you divide that by 2 pi. And you get 15.915 hertz bandwidth low pass filter. So this filter that we made that we're testing is considered a 15.915 hertz bandwidth low pass filter. So that means at 15.915 hertz, the gain will be minus 3 dB and the phase lag will be minus 45 degrees. So this is a typical first order low pass filter. If you have higher order filters, they have other ways of looking at the bandwidth. So anyway, this is a picture of our Schlumberger Solartron 1250 model 1250. So there's other models. There's a 1254 model which has 4 analyzers. The 1250 has only there's 2 channels. So I had used the 1254 before, and you could maybe do a little bit more, get the frequency response at various points with that model. And there's some smaller models. I think the 1253 is a smaller version of this, and there's various models of this, but the 1250 is pretty much the standard model. If you happen to have one of these, try to put it to use. So this is the op amp board that I made. So this is a op amp board. It's like general purpose for lab use. So this is something that I put together just to use in the lab, and it has a bunch of different kinds of op amps. Comes in handy like followers. There's differential amps and inverting amps. So I tried to set it up. I tried to break out this point so I could add a capacitor to make it into a low pass filter. The differential amps definitely come in handy when you use a oscilloscope, if I need to look at a differential signal, because the low on the oscilloscope is a ground. It's not a low, so it's tied to the house ground. So a lot of times you need a differential amp for your oscilloscope. So this comes in handy for that. Or if I need to reduce the gain or increase impedance, if the input impedance is not high enough, I use one of these followers. So this comes in handy, but I'm just using this so I could use this 1 op amp here and make it into a low pass filter. So this is a zoom in of the inverting op amp that I use, and this comes in handy. I could just put clip leads onto these nails. So these are just nails, and I take a picture, just a plot of the schematic, and I tape it to a piece of wood and I drive nails into it, and that goes to the printed circuit board. This is the printed circuit board. This is the amp here. So I could use it. It comes in handy. It makes it easy to hook up, so I don't have to think about it too hard, and I have the schematic right there. So this is the Solartron connections to the inverting low pass filter. And so this is the way I connect it. So the generator has a high and low, and these are our real differential outputs. So I just connect the high to channel 1 high, and the low, which is ground, I tie that to our common to channel 1 low, and channel 2, and this is the input going to the op amp, and channel 2 is the output. So the output goes a high, all the lows are tied to ground. So I'm going to get a plot. When I do the plot, I look at channel 2 over channel 1. So I get that ratio to get that transfer function. And you saw that when I set the thing up. When I set up the Solartron, the data output was channel 2 over channel 1. So I'm going to show you now what to do with the data. So what I have here, I made an Excel spreadsheet here for first order low pass filter. So this is something I made years ago, and I could go in here and change my tau. So if I right now our tau is 0.01, so this is for a 0.01, which is 15.915 hertz low pass filter. But if I changed it to 0.02, you could see. Oops, I made an error there. 0.02 had a comma in there, so that's 0.02, which is has more of a cutoff. If I go back to 0.01, you can see here at 100 hertz it has minus 22 dB. If I go back to 0.01, you could see it has only about a minus 16 dB at 100 hertz. So you could see at our 15 hertz, it's minus 3 dB and close to minus 45 degrees of phase lag. So this is to get our expected results. So this is idea what it should look like. But I'm going to compare the data against this, compare the test data against it. So I have the test data in this text file that I recently collected. So what I need to do is take this test data and process it and get into a form that I can compare against the expected results. So I made a template previously to do that. So what I do here, this is an Excel template that I made, and I could go, I just use sheet 2 here. So I go take this data here that I collected and go from 0.1 to 100 hertz. So hit copy and I paste it in here. So I want to break up the data, so I go to data and I go text to columns. So this is a nice little utility that Excel has. So I go delimited and just want to break it up by space. Next, so I believe it all. I just hit finish here. So now this is our frequency, and it's 10 points per decade. But I just need our gain and phase here. So I'm going to copy that. So I'm going to hit copy here, and I'm going to go to the template that I had just on sheet 1 here, and I want to paste that in. So just paste the values in. Okay, so this is our test data now. So because it was an inverting op amp, I make a little equation and subtract 180 for it to make it a non-inverting op amp, just to see it a little bit better. So I take the phase on this column and subtract 180, so that's what all these are. So now I want to go to our expected results, which was in the other file. And this is done. It's kind of neat to do this. So what you do to get the gain, it's just a formula here for a low pass filter. It's like the numerator over the square root of the say the real parts squared. So it's omega squared plus 1. You'll learn how to do this if you ever have a control systems class. And to get the phase, it's the same thing. It's the arctan 2 of the, I believe it's the imaginary over the real parts. So you could put a little formula in here to get that. That's how you get that. I don't want to go into details of that. But anyway, so we need to get our gain and phase here to do our comparison. So I copy that and I go back to our template and I want to paste that in here. So I'm just going to paste the values again. So you can see it's very close. So the red line is the expected, and the blue line underneath is what our actual test data is. So it matches very well. Our test data and our expected results match very well. So this is just a test to verify, that this frequency response analyzer is working pretty well. It compared very well against the expected results. So this is the gain, and this is the phase. So if we look at our close to our 15.915 hertz, we could see, we have the close to minus 3 dB and close to minus 45 degrees. So that verifies it. So the Solartron's a very good tool for doing frequency responses, especially out in the field, testing actuators, testing electronic circuits. It's very good with digital filters. If you need to verify a digital filter or an analog filter, it's a very good piece of test equipment. So I wanted to go through and show you how to use the Solartron Model 1250, which is a tool I have been using for probably like the last 30 or 40 years and doing my control systems work. So thanks for watching this, and I hope you learned something from this. So bye now.